Alright. So the laws of thermodynamics. Question. If I take a wine glass, or a coffee mug, push it off the table and it falls into the ground and cracks into a million pieces, can it reassemble itself and jump back up onto the table as a complete glass?
I feel like this is a trick question.
Why would it be a trick? It's absolutely possible. All of physics says it's possible. So let's look at the laws of physics. Laws of physics states that all energy has to be conserved. So whatever energy went into the system to make it jump off the table has to be conserved and transferred to the mug. When it hits the ground, it's going to push on all the molecules of the floor. The energy and momentums are all conserved. And thus, that energy is still there. That means that the floor can send that energy back into the mug. All the chemical bonds that were holding it as one piece can all reattach themselves. Whenever they break, they turn into heat, but that heat can be turned perfectly back into molecular bonds. So why don't we ever see that happen? So we have a floor, and we have a coffee mug or whatever fall onto it. And it hits and it breaks. So what's going to happen is the force of the impact is going to cause molecules to increase their velocity and energy. Where is all this energy going to be transferred to? Statistically, the most likely thing is they're going to hit another atom, and that one's going to push offward, and we're going to see the net flow of energy flow in this random direction outward, statistically. Meaning, if we were to look at the random interaction on molecule to molecule, we'd see that the net flow of energy would disperse outward into the room, heating up the entire floor and spread outward. So statistically, it's extremely unlikely for all this energy to go back. But it is possible that all the molecules that are hit will eventually bounce around, bounce off of other molecules, and start bouncing back upward. It's entirely possible that they'll rebound or bounce backward and hit the floor and with enough energy to cause the mug to bounce back up on the table. Statistically, it's extremely unlikely. But there is no reason that there's no mathematical law that prevents a coffee mug from jumping back up on the ground and reassembling itself. The only thing is probability. You have to think of how many billion atoms there are. And you have to think about their kinetic energies, their motions, and you would tend to see all the molecules radiate the energy outward randomly in all directions. And because there's a lot more directions down here, it's very unlikely that they all would radiate back to the single point of impact, forcing the coffee cup to fly upward. That's the reason why we don't see it. But in physics, it's entirely possible for a broken wine glass to fall into the ground, break into a million pieces, reassemble itself, and jump back up on the table. Even if it was full of wine, you would see it's entirely possible that the flow of wine will reverse, go back into the wine glass, and jump back up on the table. The only law in all of physics that tells us that that doesn't happen is thermodynamics. Thermodynamics tells us about entropy. The universe tends to go into disorder. If you have a highly organized situation, it tends to go to chaos or disorder. In summary, it says that energy likes to spread out. If you have a high concentration of energy in a hot coffee mug, what tends to happen is the heat energy will radiate into the room until everything's at the same temperature. So if you concentrate energy into one spot, that energy likes to spread out. Spread out. But this is a statistical. Do you know what the word statistical means?
No statistics.
So, if I flipped 100 quarters, how many will land on heads and how many will land on tails? So, it is entirely possible that you could flip 100 heads, right? How likely is that? Not very likely. But it's entirely possible. Statistically, we would estimate about half of them would be heads and half of them would be tails. Being a statistical law means that it's not always held true. It's only probabilistic, meaning it's random what happens. So it's the only law. It's one of the only laws besides quantum mechanics. Quantum mechanics is also statistical, but it's one of the main ones that aren't quantum mechanics as probabilistic. So it's a law that deals with. It's the only law that can be violated multiple times, and then we see violations in it. We only ever observe violations in it when we're talking about a few hundred atoms. For example, it's entirely possible. So every atom in this room, in the air in this room, is all moving in random directions. So they're all flowing all in random directions. They're constantly bumping into each other and bouncing off of each other. They're constantly hitting the side of the room and bouncing off. And like this. They're all moving very randomly. It's entirely possible that here in the next few minutes, the random motion just happens to line up so that all the air molecules in the room lands in the corner. This is called increasing the order, or we're having a highly ordered system by putting all the air molecules in the corner of the room, but it's entirely possible. This is like a flip of the head, a quarter. It's entirely possible that one molecule, if we follow one molecule, will bounce around and be in the bottom left, bottom right, top left. It's random where it's going to end up. Statistically, we would think that it would just be in some random spot. And once we add up the billion molecules, now everything looks the same throughout the room. We don't really see pressure gradients because we're having so many coin flips of where it's going to end up being. We have seen in systems that have like 10 to 100 atoms, we have noticed them all clumped together in the corner of the room. But that's because we now have such few atoms that statistically these major exceptions do appear up. So the science of thermodynamics was developed in early 19th century. Atomic and molecular theory of matter was not understood then, so early thermodynamics involved macroscopic ideas such as work, pressure, and temperature. That's what we've been mostly working on. Basically, back before they truly understood molecules and atoms, we could only talk about thermodynamics in terms of pressure, temperature, volume, and work. The fundamental of thermodynamics is conservation of energy. And here's the statistical thing. It's the fact that heat flows spontaneously from hot to cold and not the other way around. You have a hot coffee mug, the heat is going to leave the coffee mug and go into the room. It's entirely possible that all the collisions of the air molecules will hit the coffee mug and warm it up. That would mean the room is getting colder. We usually don't see that happen. It's entirely possible that the room would just turn freezing cold and all of a sudden my drink will start boiling. It's very, very unlikely though. The word spontaneously doesn't mean quickly. It means that it can happen on its own free will. It can happen by itself with no output energy added to it. So absolute zero is as the temperature of a gas changes, the volume of a gas changes. At 0 degrees, the pressure constant volume changes by 273. 0.15. They often round and ignore the 0.15. Absolute zero is the lowest limit of temperature. Molecules have lost all available kinetic energy, and this is impossible to reach due to quantum mechanics. Everything has to have some uncertainty in its motion. So energy at the particle level within a substance comes in several different forms. Together we call this the internal energy. This is your delta U. We usually only concern ourselves with changes of energy. The internal energy of a substance is quite complicated. We usually, because of how complicated it is, we usually only talk about changes in internal energy. We have kinetic and potential energies of molecules, and so our focus is only on the changes in internal energy rather than the total. So, first law of thermodynamics states that the heat added to a system transforms to an equal amount of some other form of energy. So, what this is the conservation of energy. So the first law of thermodynamics basically just restates the law of conservation of energy. Energy cannot be created or destroyed. It can only be transferred or transformed from one type to another. So if you add heat to a system, you're going to end up, that energy is not going to be destroyed. It's going to stay in the system. So you're going to, or it can be removed by the system by doing work. So either you're going to increase the internal energy and also the work done. Another implication, instead of adding heat, we can do mechanical work on the system. We can expect an increase in internal energy. So rubbing your hands makes them warmer. Here's the Joule's apparatus. As the weight falls, they lose potential energy mechanical, which is converted to heat that warms the water. So this was an old way of heating up water. Kobe, stay awake. So here's a question. What work is done on a system, for example, compressing air in a tire? The temperature does what? When work is done on a system, like compressing air in a tire, the temperature does what? Increases. So according to the first law, when you put work into the system, the energy is going to increase, and thus the temperature. We have adiabatic processes. Compressing or expanding a gas while no heat enters or leaves the system is known as adiabatic. Adiabatic can be achieved by two ways. Thermally insulating a system from its surroundings. Very hard to do. Performing the process so rapidly that the heat has no time to enter or leave. So the heat added to the system is zero. So the increase or decrease of internal energy is just the work done by the system. For example, when we compress air into a bicycle pump, we do work on the system, we heat the air up and increase the internal energy. So while you're pumping up the air bicycle tire, air inside is going to get hotter and hotter. That's where all the energy is going to be transferred to, is ignoring friction and stuff. So here's an interesting fact if you want to try it. If you blow out your mouth when it's wide open, versus if you pucker your lips and basically close your mouth, in which case does the air come out of your mouth colder? It's not equally cold. Which one? When you pucker your lips, the air expands as it comes outward. So when you have your lips puckered, you're compressing the air. You're compressing it to go through your the smaller gap. Thus, as it exits your mouth, it's going to have to expand. When it expands, it has to basically the outside air has to do work on it. The air expanding does work on its surroundings, so it loses. So it's pushing. So as the air expands, it pushes on the surrounding air and gets colder. This law is useful to meteorologists when analyzing weather. As air temperature rises, as heat is added, or as pressure is increased, heat may be added as incoming solar radiation, radiation back to Earth, moisture condensation, contact with ground. In the adiabatic form, no heat is added. The first law of thermodynamics becomes, as air temperature rises or fall, pressure increases or decreases. So adiabatic process in the atmosphere occur in large parts of the air called parcels. We don't really need to concern ourselves with this. We're not doing meteorology. Second law of thermodynamics. Heat itself never spontaneously flows from a cold object to a hot. Again, this is statistical. So, if you put an ice cube in a hot drink, the ice cube, or the heat is going to flow from the hot drink into the ice cube. Your ice cube doesn't make your drink colder. Your drink makes the ice cube warmer. So in summer, heat flows from the hot air outside into the cooler interiors. A winter, heat flows from the warm inside to the cold exterior. By the way, here's something for you to think about. Let's look at freezer design or refrigerator. Doesn't matter which. Let's say we have a vertical one, where the door opens like this. So you swing it open and you look inside to get to see your stuff. Versus a chest freezer. Where you open it up and peer inside. Which one is better at keeping your things colder? The deep freeze. Why? What happens when you open the door? So, cold air is denser than room temperature air. So, as soon as you open this refrigerator door, all the cold air is going to rush out. It's going to fall into the floor. So air is a fluid. Did you know that? What is a fluid? Anything that flows. Basically. So you can think of this as being full of water. You open a door, all the water rushes out. Air is a perfect fluid. Which means what rushes in is hot air, or room temperature air. And next time you go to your refrigerator, open it, wait a few seconds for all the air to rush out, and then all the warm air rushes in. Close it, wait about 1 to 3 seconds, and then try opening it. You'll find you can't open your refrigerator door. Do you know why? All the hot air begins cooling off very rapidly as it steals heat from all your milk and stuff inside of it. So this warm air is going to transfer all of its heat to everything inside of it, And what happens to hot air as it cools? Pressure goes down. And so you create a mild vacuum. You don't create a vacuum, but you create a low pressure inside your refrigerator. Which means as you go to, so if you ever close the refrigerator door and then like, nah, I do want something out of it and try to push it and it's stuck, it's because you create a low pressure in your refrigerator and the outside air is trying to pushes your door shut. Your refrigerator isn't airtight, so hot air is going to continue to seep in through the cracks until the pressures equalize. Whereas this one, when you open it up, all the cold air stays inside the deep freezer. When you close it, nothing happens. When you open it, all the cold air stays down here. So anytime you open the door, you are significantly heating up the inside of your refrigerator, if you have a vertical one. Which is why if the electricity goes out, you should minimize most definitely how many times you open it. As soon as you open it, you let all the cold air out, and you put hot air into it, and that hot air is going to steal energy, or is going to give all this energy to the surroundings. It doesn't take too many openings before you can really warm up everything inside your refrigerator. So this is statistical. Again, it's only true if you're given enough molecules for it to be statistically relevant. But basically, heat can only flow from cold to hot. By the way, a refrigerator is actually a heat generator. It's actually a heater. It makes things hot. So if we look at our refrigerator, side view, so this is the back of it, this is the front, door open. So what we have is some gas. We pump in some gas in here. That is at a high pressure. So it's a gas that boils at negative 50 degrees Fahrenheit, for example, or something. So water boils at what temperature? 100 degrees Celsius. So if I took water and let's see how to illustrate this. If I took liquid water and put it at a high pressure. So if I put this at a high pressure, I can get the water to stay liquid to about 300 degrees Celsius, for example. Because as I increase the pressure, the boiling point increases. Now, what would happen if I opened that highly pressurized water in, let's say, an oven that's at 400 degrees Celsius? Well, the water at atmospheric pressure is 100 degrees Celsius. So some of it will turn into steam, while whatever's left will turn back to 100 degrees Celsius. That's what they have inside your oven, or inside your refrigerator, is a gas that has a very low boiling point. So it's under high pressure, so it warms up to wherever the temperature inside your refrigerator is. Let's say it goes to 40 degrees Celsius, or 40 degrees Fahrenheit, and then they undo the pressure. This gas is going to begin boiling, but it's going to have to be go to its boiling point. So some of the energy is going to go into converting it from liquid to gas. So they have this liquid at 40 degrees Fahrenheit. Some of it's going to go and convert it. Some of the heat energy is going to go into making a gas, but the temperature is going to quickly drop down to negative 50 degrees. It then goes back to the back of your refrigerator, and then it's going to use a compressor to compress it back into this high temperature. and it's going to heat up to, let's say, 100 degrees, or not 100, let's say, yeah, 110 degrees Fahrenheit. Since this is way hotter than your room, it's going to eventually cool off, and that heat is going to radiate back. If you were to up, so in overall, it's taking and generating heat behind your refrigerator, which means if you open up the refrigerator and let run, all it can do is generate heat. So what it's doing is making this gas go in here. It's decreasing the pressure, which means the temperature is going to quickly go down to -50. That means the inside of your refrigerator is hotter than this gas, and so heat is going to flow into the gas. They then move it to the outside side of the refrigerator and then compress it, which forces the heat to get out of the gas and go behind your refrigerator. Same thing with your AC. Have you ever seen a portable AC? Yeah, a portable AC thing that you hook up to a window. Not the one that sits in the window. One that has like a single tube. So they have these things. It has wheels. It has a single hose, and then what you do is you put the holes at the bottom of your window, and it blows heat outward. These things are very bad unless it's your only alternative. If you live in a house that the windows can't support a window unit, and you have to get one of these barely work. The reason for this is what it's doing is it's pulling in air inside here, and then it's cooling cooling the air off by concentrating the heat and then blowing the heat outward. But if you're constantly pulling air into the unit, the pressure inside the room is going to go down, which means hot air outside is going to be forced inward because your room is going to be low pressure compared to the outside, which is going to be a higher pressure, which forces the higher pressure air to flow into your house, warming it up, making these things almost useless. There's an excellent video on it. I should put it on Google Classroom. So a heat engine is any device that converts internal energy into mechanical work. The basic idea behind a heat engine is that mechanical work can be attained only when heat flows from a high temperature to a low temperature. In every heat engine, only some of the heat can be transferred into work. This goes back to where I was talking about the Carnot engine. They've worked out that like the most efficient engine you can get is like 60 or 70%. Basically, we can, as we have a temperature gradient from hot to cold, we can extract some of the work or some of the energy as it flows from hot to cold. So every heat engine has a reservoir of heat at high temperature, a sink at low temperature. Every heat engine gathers heat from the reservoir at high temperature, converts some of that energy into mechanical work, and expels the rest of the heat to a sink at the lower one. We went in and ran my Stirling engine using boiling water at the bottom as a heat source. The top of it acts as a sink or cold, which is room temperature. And basically, as that hot air expands the gas, pushing it upward, and as the top air, it's the reverse. As the hot air pushes it downward because it flows around it and pushes it downward, the cold air cools off, causing the gas to contract, pulling the piston upward. During that, we can extract some motion by making it turn. Some of the heat is actually converted into mechanical energy spinning the wheel. Applied to heat engines, the second law of thermodynamics is stated. When work is done by a heat engine operating between two temperatures, hot and cold, only some of the input heat at hot can be converted into work, and the rest is expelled as cold. Every heat engine expels some heat. For example, the hood of your car becomes hot. Hot air is expelled from a laundry or bacon oven. So all a refrigerator does is convert. Most of all of its thing is working on the compressors. And it's just set up to where it expels the heat outside of the refrigerator behind it. It actually gets quite hot out there behind your refrigerator. So the ideal or maximum possible efficiency of a heat engine was determined by Carnot. Depends upon the temperature of the hot reservoir and cold sink. Basically what you do is you figure out the differences in temperature divided by the total or the maximum heat. And this can give you an efficiency rating. So in real heat engines, the efficiency is actually much less due to friction. But in an ideal situation, we can use this equation. So for example, let's say that I have a bottom reservoir that's at 400 Kelvin and a top one at 300 Kelvin. And I'm doing this backwards. So we can get some work out of it. What is the maximum percentage of energy we can get out? So T hot minus T cold divided by T hot. So this would be 400 Kelvin minus 300 Kelvin divided by 400 Kelvin, which is 100 Kelvin over 400 Kelvin, which is 25%. So that means that we can only extract 25% of the energy from the setup. So that's very inefficient. But it's the best we can do. Which was this example right here. So a restatement of the second law of thermodynamics. In a natural process, high quality energy tends to transform into lower quality energy. Order tends to disorder is the statement. Processes in nature, moving from disorder to order, do not occur without external assistance. So anything larger than a few atoms or a few hundred atoms, this holds true. We've only seen it in about like a dozen atoms that this statement is violated. A measure of disorder is called entropy. If disorder increases, entropy increases. Entropy can decrease if work is put into the system. Living organisms take in food or extract energy from their surroundings and become more organized. Running out of time, but basically, what disorder and entropy is like concentrations of energy. If you have a very ordered system, that means that you have all the energy in a nice configuration or all bunched together. Disorder is more random. If you were to randomize something, you increase the disorder or entropy of the system. And everything tends to go to disorder. This is the reason why we can't have perpetual motion machines. We can't continually concentrate energy at one spot because that energy wants to spread out. We also, from the first law, everything goes from hot to cold, so due to friction and stuff, we'll go into more examples tomorrow of why perpetual motion machines can't exist, how they violate these laws. And again, it's only true for things bigger than a few atoms. We have designed some nanobots that can violate this law and basically self-power themselves by statistics. Most of the time they do nothing, but randomly they can extract energy from the randomness around them and start working again until they run out of energy, and we wait a little bit, and then eventually random bumps into them will give them enough energy to continue working again.